Welcome back. So, in this lecture we are going to discuss the third part of canonical ensembles, where we have already seen that under a given condition of temperature, volume and number of particles, if I know the partition function, I can get the thermodynamic properties where the relationships are given listed over here: the Helmholtz free energy, average energy or the internal energy, entropy, pressure and even chemical potential. So, all these require the partition function Q as a function of temperature, volume and the number of particles. And obviously, you understand that for a given system, capital Q, that is equal to summation over all possible microscopic states e to the power of minus beta E I, where E I characterizes the ith microscopic state as given by the solution of the Schrodinger equation. So, therefore, the aim of this particular lecture is to evaluate the canonical partition function of a given system for which the solution of the Schrodinger equation is known. So, we are going to start by calculating the canonical partition function for single particles. We have already seen a lot of single particle systems for which we have discussed in detail the solution of the Schrodinger equation and how to count them when they are present under the isolated condition. Now, we are going to use those concepts once again in this particular course. So, the first application that I have in mind is a single spin half particle. Okay? And in this case, unlike the isolated system, I have this system which is immersed in a thermal reservoir, and here for the sake of simplicity I have a single particle. And this single particle in my first example corresponds to a spin half particle. I assume that there is embedded inside the system some magnetic field H. Therefore, if the magnetic moment associated with this spin half is mu, in that case I know that from the solution of Schrodinger equation for the isolated system, the allowed energy eigenstates for this spin half particle is going to be the first one, the spin up microstate having an energy minus mu h, and the second one which is plus mu h energy having a spin down, that means the spin is oriented antiparallel to the direction of the applied field. So, how many microstates are there under isolated condition? There are basically two such microscopic states. Now, when you take any such system and put it in contact with a thermal reservoir, now we are asking the question, are they equally probable? Because of the presence of a finite temperature, you are no longer in the temperature-less description of the Schrodinger equation, and therefore, the two possible microstates are going to be differently populated under the condition of finite temperature. And then correspondingly, we will say, well, since it is a single particle system, I am going to use small q as the representation of the canonical partition function for the single particle, and this is going to be by definition once again summation over I e to the power of minus beta E I. Now, how many microstates are possible for this system? 2. So, I will say this is I equal to 1 to 2, and accordingly I will write in this summation in the expanded form and say that this is equal to e to the power of minus beta E1 into e to the power of minus beta E2. I know for this given system what E1 is. This quantity is minus mu h and this quantity is plus mu h. Therefore, I can very easily write down that small q is equal to e to the power of minus beta mu h plus e to the power of, this one is plus beta mu h and this is going to be minus beta mu h. As discussed in the last class, I am using this particular notation, that beta is equal to 1 by the Boltzmann constant multiplied by the temperature in the absolute scale. Now, once you know this small q, I can very easily answer questions like, what is the probability that this single particle in this system has an up spin? Then obviously the answer is e to the power of up spin, which means that is the first energy state that I am talking about. So, that is minus beta of E1 divided by q. By definition, Pi is e to the power of minus beta Ei by q. So, here my up spin corresponds to the index 1 here, and therefore, I am writing it like this. So, writing it explicitly, then I have this is equal to e to the power of beta mu h divided by e to the power of minus beta mu h plus e to the power of minus beta mu h. Clear? So, that is the result that we have put up here. So, this is actually trivial, I would say, and this can be extended very easily to the general scenario of a two-state particle, where instead of having minus mu h and plus mu h, I would say that my system is comprised of a single particle for which the energy state diagram from the solution of the Schrodinger equation is like this. So, once again, how many microscopic states are possible for this system? The Schrodinger equation solution tells you that only 2 microstates are possible. And what are these energy values or energy eigenvalues for these 2 states? One is E1 equal to 0, the other one is E2 is equal to epsilon. So, once again, if I write down the single particle partition function for this system, I will say that this is equal to I equal to 1 to 2 e to the power of minus beta Ei. So, as before, I am going to write it as e to the power of minus beta E1 plus e to the power of minus beta E2. Now, I put the values of E1 and E2. So, e to the power of minus beta epsilon. So, what is the final form of Q? The final form of Q is 1 plus e to the power of minus beta epsilon. Okay. So, this is basically a generalization of what I had from the spin-half particle system. So, here as you see that I have 2 distinct microscopic states, and the corresponding partition function for this single particle is this. So, if I ask you the question, what is the probability that this particular microscopic state will be observed? That probability corresponds to my energy E1 equal to 0. Therefore, the probability of observing the system in the lower energy state, which has an index 1, that is equal to e to the power of minus beta E1 by q. Now, what is E1? That is 0. So, this term becomes 1, and I have 1 plus e to the power of minus beta epsilon. Similarly, if I want to know what is the probability of observing the system in this particular microstate, that is where the system is present in the upper energy state, in that case I would immediately say that the probability is e to the power of minus beta epsilon divided by 1 plus e to the power of minus beta epsilon. Okay. This is a repetition from the last lecture, but I thought I will highlight it once more before we take up other examples. But there is one more example that we have talked about in the last class, and that is the simple harmonic oscillator, where unlike the first 2 examples, I have an infinite number of solutions of the Schrodinger equation possible, and with a given angular frequency of the oscillator. So, in this case, when I write down the energy states, I write it down in terms of a quantum number that varies from 0 or 1, 2, etc. So, it can take up integral values, and there are infinite number of possibilities. For a given value of this quantum number v, you can find out the associated energy value of this energy state, and that is V plus half h cross omega, where omega is the angular frequency of the oscillator. And therefore, once again, since the basic definition of small q is summation over all possible microstates e to the power of minus beta E I. So, in the case of simple harmonic oscillators, each microstate is characterized by this one quantum number V, and therefore, here summation over all microstates, as I always write here, is actually a summation over all possible values of the quantum number V. Okay. So, following this principle, we have shown you how to derive this, how to evaluate this infinite summation, and we find that there is a very nice analytical expression as shown over here. Now, in today's class, what I am going to do is, I am going to talk about a particle in a one-dimensional box in thermal equilibrium at a temperature T. Now, once again, this is the picture that I have in mind. So, I have a three-dimensional box. Okay. So, I will consider only one direction in it, so that the particle is moving in this direction, which is probably the x direction, and it moves, it has to confine itself between 0 and A. Okay. There is only one such particle, and this box, or whatever this direction is, this is in equilibrium with a thermostat maintained at a temperature T. Okay. So, I have n equal to 1. Instead of volume, since I have a single dimension, therefore, I have a length that is equal to A, within which the particle is confined, and the other thing that I require to define the macrostate of the system, that is the temperature T. Now, the question is, how shall I obtain the canonical partition function for a particle like this? So, let us remind ourselves what is the solution that we know from the solution of Schrodinger equation for any such system. We know that once again all the microstates can be described in terms of a single quantum number, which is n. So, what are the possible values of n? N must be an integer varying from 1 to infinity, and the corresponding energy values are given by n square multiplied by something which depends on the Planck's constant, mass of the particle, and the length A over which it is confined. So, it is possible to use this relationship and evaluate the small q for this system. So, small q now, just as before, would require a summation of this particular term, exponential of minus beta into energy values over all possible microstates. Here each and every microstate is characterized by the quantum number n. Therefore, a summation over all microstates translates to the summation over all possible values of n. Now, n starts from 1 and goes to infinity, right? And therefore, I would say that in order to be able to evaluate this q, we need to evaluate this particular expression in keeping with the known solution of Schrodinger equation for a particle confined in a one-dimensional box. Now, but it should be easy to do. Once again, we are having this problem of evaluating an infinite series summation. But unlike the previous case of simple harmonic oscillator, what we find is here the summation is not so easy. And why do I say so? That is because, let us say that I am going to calculate evaluate this sum by hand. Can I do it? I mean, infinity is a very large number. So, it is not possible to do this summation by hand. You might argue that I can use a computer to do this summation. So, even in that case, you will have to specify the maximum value of n up to which you are going to add to this evaluation of q. Now, my small q is a number like say summation over n going from 1 to some n max, say, for the purpose of my actual summation of this, e to the power of minus beta E n. Okay. Now, if I do this summation, then I will have e to the power minus beta E 1 plus e to the power of minus beta E 2 and so on and so forth. Let us say that I will go up to e to the power minus beta E n max. If that is so, then there will be other terms as well, which will correspond to the value of n greater than n max, something like n max plus 1. Okay. Now, if it so happens that I can truncate it at this position and ignore any of these terms which are present, that will give me a rather accurate evaluation, numerical evaluation of this summation, and thereby give me an estimate of accurate estimate of small q. So, the question that I have here is E n max, beta E n max, when it is exponentiated like this number must be much less than 1, so that whatever other terms are there in this particular summation, they are going to be very insignificant. I mean n max or n max plus 1, this kind of relationship is going to be very small, or in other words, I must be having beta E n max must be much greater than 1. Actually, if you look at what are the possible values, for example, say beta corresponding to a temperature of 300 Kelvin and mass is about 50 AMU, and if your A is roughly, A cube is roughly about 22 liters, what you will find that this n max value is going to be roughly of the order of 10 to the power of 20. So, of course, then there is a very large number of terms that I need to find out, I need to add in order to be able to evaluate this infinite series summation. Of course, I am not going to do it. The scientists are very smart people, so they found out alternative ways of evaluating this sum, and that is as follows. So, what they did was they understood that this series summation can be replaced by an integral. Now, when you do this, you understand that you are dealing with a situation where you are plotting, say, x along this direction and f x along the y direction, and let us say that this is how f x varies as a function of x. Now, what we are trying to say is x varies from some initial value 0 to some final value here, that is, say, x t, right. So, basically what we are looking for here is we have discretized the x direction into a few different values like x 1, x 2, x 3 and so on and so forth. And what we can do is we can find out the corresponding values of f x at these points. Now, why is this discretization important? This discretization is important because if you find out the values of these rectangles, areas of these rectangles from here in this figure, then that is going to give you a rough approximate value of the area under this curve. Okay. So, and that is exactly what we would look for, but this depends very much upon the interval that you have chosen over here, and this interval is something that decides whether the sum of the areas under this rectangle are going to be accurate enough to represent the integral. And we already know that yes, this is true if and only if this interval is very small. Now, if you go back and look at like the typical values that we are thinking of here, we are finding that I am going to look for dn e to the power of minus beta n square h square divided by 8 m a square, right. I am going to evaluate this. So, which one is my fx? My fx or my fn here, that is equal to e to the power of minus beta n square h square divided by 8 m a square. Okay. Now, so in this particular case, the n appears with all these numbers, and if you go from n to n plus 1, the delta, that means the change in the values of n, the corresponding functional change, that is of the order of 10 to the power 10 minus 10. So, which means that I can indeed replace the summation that I have written here in terms of this integral, okay. And it is possible to evaluate this integral, and do you know how to do this? I will quickly have a look at how to do this integral, and the result is something that I am going to show you first. And the result is something like this. So, what is lambda t? Lambda t is a quantity which we will see that it is very important as far as describing the temperature dependent properties are concerned, and this is known as the de Broglie wavelength, and it has the dimensions of length. Now, going back, let us now try to do this particular integration. So, q is equal to 0 to infinity dn e to the power of minus beta h square divided by 8 m s square into n square. Okay. Now, what I am going to do is, let me use the following notation. Let alpha be equal to beta h square divided by 8 m s square. Then this integration now looks like 0 to infinity dn e to the power of minus alpha n square. Okay. I need to find out the value of this integral. In order to do so, let me do further assumption. Let me say that y is equal to e to the power of minus y is equal to alpha n square, right. So, what is n square? N square is equal to, so what is n square? N square is equal to y by alpha, right there. And now, since I know y, I can find out what dy is. Dy would be alpha into 2n into dn. Now, I am going to finish doing this change in variable and say that then dn is equal to 1 by 2 alpha into 1 by n into dy. Now, what is n? N square is equal to y by alpha. Therefore, n is equal to alpha to the power of minus half into y to the power of half. Now, I put everything together. So, what I get is dn is equal to 1 by 2 alpha. Then, in place of n, I am putting in alpha to the power of minus half into y to the power of half into dy. A little bit more of algebra, and then what I find is that I have here half alpha to the power of half y to the power of half into dy. Now, I am going to use these new variables in order to find what small q is. Now, when n is equal to 0, what is y? Y is equal to 0. So, this is the lower limit replacement. When n is equal to infinity, once again alpha is a finite quantity, it is non-zero. As a result, this stays as infinity. Instead of dn, I am going to write it as 1 by 2 root alpha into y to the power of minus half dy, and I am going to do the replacement here and this is equal to minus y. So, this now turns out to be 1 by 2 into root alpha into integral 0 to infinity dy y to the power of half minus 1 into e to the power of minus y. By now, you must have learnt in your maths courses that this is nothing but 1 by 2 root alpha into gamma half, right. So, my small q now turns out to be 1 by 2 into root alpha into gamma half. Do you know what the value of gamma half is? Yes, the value of gamma half is root pi. So, what I have here is pi divided by 4 alpha to the power of half. Okay. Now, I do know the definition of alpha, and that is equal to h square divided by 8m a square into kBt. I put it back over here. What do I get? I get this is pi divided by 4 into h square into 8m a square kBt to the power of half. Okay. So, the final expression that I get is 2 pi m kt by h square to the power of half, and I have taken the a outside. Now, this is the quantity that I am going to use, and you can very easily confirm that it has the dimension of length. And I am going to inverse of length, and I am going to define lambda as lambda square as h square divided by 2 pi m kt. So, what is the final expression for q? That is equal to a divided by lambda. Now, have a look at the definition of lambda. Lambda is a function of temperature. So, where does the thermodynamic information enter over here? It enters here in terms of the temperature. And does it depend on the volume? No. And therefore, I would say that lambda is a function of temperature and temperature only. It does have a dependence on the system property. Can you identify which system property it is depending on? Yes, it depends on the mass of the particle which constitutes the system. Okay. So, lambda, this is known as the de Broglie thermal wavelength, that is giving us the temperature dependence, explicitly the temperature dependence of the single particle partition function in this treatment, and that is exactly what we have shown here. Now, what happens if I have the single particle, but it is not present in a one dimensional box, but it is present in a three dimensional box? Okay. So, in that case we would use the same type of argument, because I would say that now each energy level is identified in terms of three quantum numbers nx, ny, nz, and these values are h square by 8m a square into nx square plus ny square plus nz square, right. And therefore, I would say that this is nothing but Enx plus Eny plus Enz. That is because whatever happens in the three orthogonal directions, they give you three independent degrees of freedom, and therefore, I can write the total energy eigenstate in terms of three independent contributions. So, what is small q? Now, small q is summation over all possible energy eigenstates into e to the power of minus beta Ei. Now, this can be written very easily as summation over all possible values of nx e to the power of minus beta Enx. Similarly, this is ny into e to the power of minus beta Eny, and the summation also goes over nz giving you e to the power of minus beta in z. As you see, these are dummy indices, right? All of these three summations are the same. Okay? So, I can very easily write that essentially what I have is, I need value of this summation e to the power minus beta E n whole cube, the same summation being assumed 3 times in multiplication with each other. Now, do you know the value of this summation? Yes, we did that for a one dimensional box right now, and therefore, what I will have for a particle in a 3 dimensional box is this, that small q is going to be equal to a by lambda for the x direction, a by lambda for the y direction, and a by lambda for the z direction, or in other words, I can write it as v by lambda cubed, where I have assumed that I have a cubic box such that v is equal to a cube, and by definition lambda square is equal to h square divided by 2 pi m k t. So, in the last class I have talked to you about how to write down the canonical partition function for capital N distinguishable non-interacting particles as capital Q is equal to small q to the power of n. So, there you had n one dimensional systems that are independent of each other, and today I have shown you 3 independent degrees of freedom associated with one particle. So, once again what I found that for every independent degree of freedom you have one small q contributing to the overall capital Q. Now, we are going to use these ideas and look at the application of whatever language that we have developed over here and start talking about systems that we see every day. So, from the next class onwards, we are going to see the application of the introductory concepts of molecular thermodynamics that we have developed here. Thank you.